All right, so let's continue our discussions. And so as we know that ESC201P Electronic Circuits Laboratory, what we are doing is using circuit simulation using the microcap tool to understand and design circuits. So in this experiment number 5, lab number 5, what we're going to do is look at power supplies using a half-wave rectifier, and we'll use simulation to understand how the power supply works, what is the behavior of the diode, and we'll design it for a particular set of specifications. And then what we'll do is we'll use in part B, we'll use a power supply which uses a Zener diode also. So all right, so let's start with the first part here. So in the first part, what we have to do is design the DC power supply, which is shown over here. So this is a transformer. The input is a AC input, the usual AC input that we get, 220 volts RMS, which translates into 311.127 peak value here. The frequency is of course 50 Hertz. So that's the AC input. So we use a transformer to step down the voltage. And our goal is to obtain a DC voltage equal to 5 volt at the output here. DC voltage equal to 5 volt, and the load current is 100 milliamperes. Okay, so it's a 100 milliampere 5 volt charger that is there here, right? And so the AC output that we get from the output of the transformer, that is rectified, half-wave rectification through this particular diode, and the capacitor is used to generate a DC, but of course that's not a perfect DC. We get a ripple, and if you go back to your notes in ESC201, you can see that the ripple voltage can be written in a simplified form by this particular expression here. Vm is the peak amplitude of the output voltage here, F is the frequency, RL is the load here, and C here. So in our case, we have a current source here. So basically Vm by RL, output voltage by RL, is nothing but the load current here, 0.1 here, and F by C here. So what we have to do is design the power supply such that the output voltage is 5 volt, the load current is given 100 milliamperes, and we are given a specification that the peak to peak ripple is less than 50 millivolt here. All right, so 50 millivolt ripple here. Now, as part of the design, then what is remaining is that you have to determine what is the transformer turns ratio and what is the appropriate capacitor value here, and use the simulation to understand how the power supply works and also to fine-tune the design, right? So that's the first part of the experiment. So let's open up the simulator and see some aspects of this particular design here, right? So this is our microcap simulator, and this is what we have to do, and the circuit has been constructed here. So note that our specification is 50 millivolt ripple. So if we peak to peak, if we put 50 millivolt here, and IL is given as 100 milliamperes, F is 50 Hertz, so we immediately get the value of the capacitor. And so I think the capacitor value turns out to be 40 millifarad here. So we can put the capacitor 40 millifarad here. All right, so that's the part here. The other thing is we need a 5 volt output here. And if you start with a very simple design, assume that there is a 0.7 volt drop across it. So what you need is a 5.7 volt peak value of the AC voltage here. So here on this side you have 311.127, and on this side you require 5.7. So this is the the gain of the transformer, or the turns ratio, the number of turns in the secondary divided by number of turns in the primary. So gain is 0.0183, right? So that's a very quick design that you can obtain assuming a 0.7 volt drop and using this particular expression to calculate the value of the capacitor here. All right, so then after obtaining the design, well, you can do the simulation to explore how the design works here. So what we're going to do is look at the output, which is node number 12 in this particular case here, and the input, we'll look at the transformer output here, which is 11 here, and we'll do transient simulation. And note that we are not really interested in the initial, when you switch on the whole thing, we're not really interested in the initial part there. We are interested in steady state part here. So let's do the simulation here. So let's do transient. And note that one cycle, because it's 50 Hertz, so one cycle is 20 millisecond. So I'm going to let it run for 100 millisecond 5 cycles. And I'm going to ignore the first few cycles. So I'm going to look at the last 2 cycles here. So I'm going to start plotting from 60 millisecond to 100 millisecond here. Okay. And as usual, we will do auto scale. And what we are looking at is the output voltage is V12 and the input is V11. So note that V12 and V11. Okay. Transient limits here. So that those are the 2 things that we're going to plot here. All right. So before that, let's check the input here, whether our input is proper or not. So let's plot V11. Right. So we had expected the transformer turns ratio was adjusted to get 5.7. So we can find out instead of moving the cursor, what we can use is that this will tell you what the peak value is. So this is 5.694. So that's okay. So the transformer is generating close to 5.7 here. So that's fine. Let's look at the output here. So let's enable the output is V12. So let's enable that also. And let's see what it gives here. All right. So this is what and different scales are used for the 2 plots here. So this blue line shows what the output is. And we can see what the output is. We can use the peak value here. All right. So it's showing peak value is 4.8. And let's use to get the ripple. So from here to here is the ripple. We can use the negative peak here. So it's going from 4.819 to 4.77. So the amount of ripple, peak to peak ripple, is it's taking a difference. This is the right cursor 4.773, left cursor 4.819, taking the difference here. So 46.27 millivolt, and our specs was 50 millivolts. So that part is fine because we have chosen the value of the capacitor properly. So it meets the specs of the ripple. But note that the value starts from 4.8 and goes to 4.77. So its average is about, because the ripple is very small, so the average is about, let's say, 4.8 only, right? So 4.8 is the average. Now, why has the average fallen to 4.8? Input we have chosen as 5.7, but the output is 4.8. And the reason is that the diode drop, which we assume to be 0.7, is not really 0.7. The diode drop is something else, and that depends on the nature of the diode that we have used here. And it's for that reason that the value is not really 5 as we had expected here. So if we go back and look at it here, we have used the diode 1N5401. The diode, this particular diode has enough current to supply the load here. And so we can study this particular diode here. If you wish, you can study this particular diode and look at the nature of the diode here. And so that is something that you can explore, because what has happened is we used transformer turns ratio to get 5.7 here, but what we are getting is 4.8 here. So we are getting actually a diode drop of 0.9 volt here. So if you wish, you can explore the diode drop a little better here by using the diode IV. So you can make a simple circuit like this with the diode here. It's the same diode, 1N54001. It's the same diode here. Before that, let's for the time being close the transient analysis here. And let's go to the diode part here. And what you can do is you can explore the diode here by doing a DC analysis of this particular diode here. So we're going to plot the current flowing through this diode versus the voltage here, right? So let's look at the IV characteristics by doing DC simulation. So I'm going to plot ID2 versus the DC input. So I'm going to use diode voltage here. Where is VD here? All right, VD here. And I'm going to vary from, let's say, 1 volt to, let's say, 0.2 volt with a step of 0.01. All right, so let's do that. And let's run. So it's auto scales, should be okay. All right, so that's how our diode looks. Okay, so it's taking some time because the number of points are large. right, so it's best to see the diode's characteristics on a semi-log axis here. So let me stop it here for a moment, and let's cancel this here. So let's go DC limits, and maybe we can 0.9, and I can increase it to maybe 0.2 to limit the number of points. And let's plot it such that the y-axis is log scale here. All right, okay, let's run it here. So note, this is how a diode looks like. So this is the part that is the exponential part that is there here, right? The exponential part. So we can use a cursor and explore. So depending on at what current your diode is operating, you have different diode drops here. And note that at very low current, you don't have a proper exponential. You have some leakage currents and all that here at this point here. But at higher biases, you have this thing here. So we were thinking of operating it at 100 milliamperes. So let me go to 100 milliamperes here. Right now it is, so one way of going to a particular data point is by looking at, I think this point here. So go to a particular Control Shift Y. So if you press this, you can go to a particular value. So let's say 100 milliamperes is 0.1, and we want the left cursor to go there, right? So it is here. So 100 milliamperes, the diode drop is 0.769. So it is not exactly 0.7 volt, but it's not too far from it also. It's not too far from it here, because we can see points, it's only 0.77. But when we were making a power supply, we were getting a diode drop of, it appeared because we had used 5.7 as the transformer output, and we were getting 4.8, so we were getting almost like 0.9 volt drop here, right? And if we go back, so let's close this. If we look at 0.9 volt drop here, 0.9 volt drop is requiring a current of 3 amperes here, right? So why is such a large drop occurring in the diode? Why is 3 ampere flowing here? And so anyway, so you can look at the diode's characteristics through this particular plot, and you can study it. So let me close this part here, and we can go back to a power supply here. We can go back to the power supply here and find out, for example, let's again show the transient analysis. So let's run it again here. So look at that here, right? So this is going to 4.8, even though if we go on this side here, this voltage here, peak value is 5.7, right? So, but it's not giving us 5 here. So there's more drop occurring. So what you can do is you can look at the diode within the power supply. What is really happening to the diode within the power supply? So note that what happens is the diode is really switching on here at this particular point. The switching on here, and the diode is on for a very short period of time. Only during this period the diode is on, right? So you can plot what is happening to diode voltage and diode current. So for example, if we look at diode is D6, so we can look at the diode current here, right? So let's go back here, transient limits here. Let's keep here, all right, let's keep both of them, and let's look at ID6, right? The diode current. So let's enable this here. Look at that here. The diode current is flows for only very short period of time here. And we can look at what is the peak diode current here, right? We can again use the peak value. So note that the diode current is going up to 2.8, almost 3 amperes here, right? Because the diode is conducting for a very short period of time. And in that short period of time, it has to supply the entire load current of 100 milliamperes. So 100 milliamperes is flowing for almost the entire period, but the diode has to supply because the source is through the diode, right? So it's 3 amperes here. And we saw, if you remember, the diode characteristics around 3 amperes, we had 0.9 volt drop across the diode, right? So the diode is, you can see the thing here. So the other thing is when you choose a diode, you know, for example, you may make the mistake of choosing a diode on the basis of the load current. You may think that the average current that is flowing in my load is 100 milliamperes, so I should choose a diode which is capable of 100 milliamperes. But when we do the simulation, we can see diode current goes as high as 2.8 or close to 3 amperes here. So you should choose a diode which is capable of this 3 ampere current pulses on a repeatable basis here, right? So there'll be pulses like this here, another pulse like this. So these pulses of current would be flowing here. Anyway, so you can explore all of this through the simulation. So the other thing that you do is that happens is that you do a design on the basis of a simplified model, right? So we used a 0.71 model here, and we use this particular equation, and we run the design. We simulate the design. We find that it doesn't meet the specs. We wanted 5 volt at the output. We are getting 4.8, right? So let's close this aspect here. So you can even switch it off by here. You can do that. All right. So we are only getting peak value here. So let's see. We are only getting 4.8 here. So what we need to do is now fine tune the design. We need to go back, and what we know now is that 5.7 volt here at the output, secondary output, is not enough. So we need to fine tune it so that we get maybe 5.9 here at this particular place, and then you will get close to 5 volt here, right? So some fine tuning is required because the initial design is based on a simplified model, and when you run the simulation, the simulator uses a more accurate diode model, and therefore some fine tuning is required here. So you can see all of that here, and what we would like you to do is find out a proper turns ratio, transformer turns ratio, so that you get a final value which is 5 volt, and the ripple is also less than 50 millivolt here. So that is what we are looking for. So carry out the design. You can use the simulator to study diode current, diode voltages, all of that you can explore. Now, one of the issues with this particular design is that we are using, to get 50 millivolt ripple, we get a 40 millifarad capacitor here. So that's a very large capacitor. And what we would like to do is, we would like to reduce the value of this particular capacitor to make, let's say, the power supply more compact. So one way of doing that is by using a Zener diode. So using in this particular manner here, right? So it's the same power supply, but what we have is, so we have a load current here, but in between the output of this capacitor here, we put a Zener diode regulator. So that's also something that you've studied as part of ESC201. So we use a Zener diode regulator, and Zener diode, it acts like a constant voltage source. And so that should help us in generating a constant voltage here. So all the burden of, generating a constant DC voltage is not on the capacitor. Earlier, the capacitor had to filter out all the higher harmonics and generate a DC. Now, part of the burden is shared by the Zener voltage here. So what we would like you to do is redesign the power supply now with a capacitor that is 1/10 of the previous value. Note that in the previous case, we are using 40 millifarad. Now we would like you to use a capacitor which is 4 millifarad. Now, if I didn't use the Zener diode regulator, and if I remove R1 and Zener diode regulator here and simply put the current source, if I use 4 millifarad, I will get a ripple which is 10 times higher, right? Because it's inversely proportional to the capacitor. So if I use a capacitor which is 10 times smaller, the ripple will become 10 times higher. So instead of 50 millivolt, we'll get 500 millivolt, right? So now we will get about 500 millivolts of ripple here, but then we would like to use the regulator here, the Zener diode now, to bring it back to 50 millivolt kind of a range of ripple here. So this is what we have to do in this particular case here. Again, we want 5 volt DC, load current is 100 milliamperes, ripple needs to be 50 millivolt. Capacitor value is 1/10 of that obtained in part A, which is 4 millivolt here. Now, as part of the design, the only unknowns are the resistor here, the transformer turns ratio here, and normally as a designer, you would also have to choose a particular Zener diode. So in this particular case, we have given you a Zener diode 1N4733. So use that particular Zener diode. It has we will just see its characteristics. And so you have to use that to figure out now the remaining parameters and make this particular circuit work. So let's look at this particular Zener diode, right? So Zener diode IV we can study through by taking the same Zener diode, let's say attaching a voltage here and a resistor here, and we can look at the IV characteristics here. So basically we are looking at the Zener current, which is D5, versus the voltage V10. All right, so let's close the transient. Let's run the DC again. Let's go back here. Let's run the DC analysis again. But this time we are looking at ID5 analysis DC. ID5 versus V10, right? So let's put V10 here. Okay, and let's disable this part here. Let's enable it here. Let's look at VZ input here, and let's give from 10 to, let's say 10 to, all right, so 10 to maybe 2 volt here. Let's do it at an interval of 0.2. Let's see what it does. Okay, so we are looking at Zener diode characteristics. All right, so this is what we get here, right? So when we run it here, this is the Zener diode characteristics, and note that Zener diode characteristics, so we have applied a voltage. You can go back and see the voltage that we applied. We are applying a voltage, so it's under reverse bias, right? So it's constant, and then this is the characteristics here. So this is supposed to be a Zener diode's rating is Zener voltage of 5.1 volt here. So this is where it is. So what you can see here is, if you use a cursor, so this is the Zener mode here. So you would like to operate in this particular mode here. So we would, make sure that the minimum current that is flowing in the Zener is at least 10-15 milliamperes. Then you are in this particular range. It will regulate properly in this particular range here. So 10, maybe, let's say you are here. So minimum current is 20 milliamperes, maximum current maybe 100 milliamperes, but note that the output voltage goes to 5.5. You don't want to, so you would like to be here. You would like to be, let's say 5.04, where the current is 40, and maybe, depending on the how much the change across the Zener voltage. So somewhere here is where you would like to operate in this particular range, because we want output voltage to be 5 volt and the ripple to be around 50 millivolts. So somewhere here is where, so this much amount of current should be flowing across the Zener. The other thing is, note that practical Zener diodes don't have an abrupt value here. The Zener diode has a resistance here. So there is a slope here. So we can easily see the slope here. Slope of this particular one is the change in the current divided by the change in voltage. So it's 135.983. If you take an inverse of this, you'll get about 7 ohms here. So the Zener diode has a series resistance kind of a thing, and so it's about 7 ohms here. So that's something to keep in mind. It's not a perfect Zener diode with an abrupt characteristics, right? So we need to take that into account, and we need to work under this particular current range here, around this 5 volt that you see here. So for a Zener diode to have 5 volt across it, you need to have around 40 milliamperes or so flowing through it. Okay, so this is what we learn about this particular Zener diode, and it has a series resistance of 7 ohms here. So let's leave this and come back to our circuit. So when we come back to this particular circuit here, so note that what we are doing is we are using 1/10 of the value of the capacitor. So the amount of ripple at this particular node here, at this, which we calling it the voltage across the capacitor here, VC2, that's the ripple here, which means that the change in the value of the voltage, right? That's going to be 10 times higher. So we want 50 millivolt multiplied by 10, because we've used 1/10 of the capacitor. So ripple voltage is around going to be 500 millivolt. And at this point, we want a ripple voltage of 50 millivolt here. So if we do a simple small signal analysis of this particular part, there's a resistor R1, and this has a resistance of RZ, the Zener resistance. So the output voltage, the ripple at the output, can be written as the ripple at the input here, and it's a voltage divider R1 and RZ, so RZ by R1 plus RZ here. So that's sort of, we know that it's going to be around 500 millivolt, this is going to be 50 millivolt is what we are looking for. So that sort of tells you, and RZ is 7 ohms, that sort of tells you what kind of R1 you should choose here, right? And the other thing is, we need to make sure that we have enough voltage here, enough voltage that is generated at this particular point, so that we can supply 100 milliamperes of current. And also about, we saw that for a Zener to operate properly, we need about 40-50 milliamperes of current here, right? So 40-50 milliamperes of current here, 100 milliamperes of current here. So that much amount of current should flow here. and if you know the value of the resistor here, so from there you can get what is the value of the voltage that I require at this particular node. And from there you can figure out what is the value of the voltage required here, and that would tell you what is the transformer turns ratio here. So you'll have to do a little bit of iterations, trial and error, to figure out what is the right transformer turns ratio, so that the whole circuit works fine now and gives you 50 millivolt of ripple through the use of this particular diode at a much smaller value of the capacitor here, with 1/10 of the value of the capacitor here. Right, so you can, so we would like you to design this and use the simulator to understand and fine-tune the design based on this, based on a Zener diode regulator as well. All right, so these are the two parts to this particular lab here, A and B. And so learn all about power supply. So we've kept the power supply simple. We could have used a a full wave rectifier, we could have used a bridge rectifier, many other things, but these two circuits they provide you with basics of you can learn about power supply through these two examples here. All right, so let's stop here.